Good afternoon. My name is Dave. I'm with a restoration group from Astoria, Oregon. We're restoring a 1925 Baldwin steam locomotive. AstoriaRailroad.org is our website for the history and the pictures. We're a 501c3 nonprofit association. We're all volunteers working on the locomotive. All volunteers are welcome. All donations are also welcome. This is a picture of the locomotive when it was running in Santa Maria Valley in California. Today we're going to install a crank stub shaft into a driver wheel on the locomotive. The shafts are located in these positions here. This particular locomotive is a 282, which means there's two wheels in the front, 8 drivers, 2 wheels in the back underneath where the engineer sits. On the side here you can see the shafts that run from the steam cylinder here that drive those driver wheels. So you have the steam cylinder here, you have the steam valve here. The steam valve directs the steam from the front of the piston to the back of the piston. That's what makes it all work. Okay, here's what we're going to do. Again, there's AstoriaRailroad.org. That's our website. What we're going to do specifically is we're going to insert this portion of the shaft right here into a driver wheel. Now, in order to get that into the driver wheel, we have to shrink it. We have to shrink fit it or freeze set it, because the diameter of this has to be 4/1000ths of an inch over size of the bore. That's a standard that you would use to create a shaft like this if it's an interference bore. So in our case, our bore diameter is 4.577. The shaft diameter is 4.581. So, and we also have a radius right here that keeps the shaft from going any deeper than that into the driver wheel. Back here we have an inset cut with a chamfer of 45 degrees that's riveted over after the shaft is put into the driver. So here you can see the diameter again, 4.581. The length of the shaft is 10.5 inches. And the front portion of this is the bearing surface for that crank rod that makes the driver go around. This particular shaft also has a 1-inch hole in it because there's a big long bolt that goes through there that clamps a washer on the front here to keep that driving rod from coming off. So in this case, the freezing is going to occur from the inside and the outside, which will probably make it a little faster cooling down. Now, liquid nitrogen is what we use to freeze it with. Liquid nitrogen gets down to minus 196 centigrade or minus 320 degrees in Fahrenheit. So that's mighty cold. So the next process that you'll see is us shrink fitting it. And by the way, steel will shrink 1.9 thousandths of an inch per inch of diameter at minus 320. So we can get quite a shrinkage there. Okay, here we're uprighting the driver wheel, and John and Scott and Martin are setting it up there you'd want to try to get the thing level as much as you can, because we're going to use gravity to drop that shaft in. They're quite heavy, so you can't just stick them in by hand. And here Scott's got the shaft here. We're going to set it down and spray some stuff on the top there to protect it from moisture. And Martin's going to shield the bottom part, because you don't want that stuff to get on the bottom, because that'll inhibit putting the shaft in the bore. And there's the freeze tank. That's where we put the liquid nitrogen in the shaft. About 22 inches tall, insulated inside with foam, and the inside is stainless steel. We use stainless steel because when you put liquid nitrogen in there and freeze it at minus 320 degrees, it gets brittle. All the welds get brittle, so you don't want anything snapping on you. And here's another picture with the liquid nitrogen tank there. It's made out of stainless steel. Has a pop-off of 22 psi, which means that the inside of that tank pressure never gets above 22 psi. Liquid nitrogen is always off-gassing. So you'll see here after we put the stuff in the tank there, or the freeze tank there, it's going to be vaporizing into the atmosphere. John's measuring the outside diameter at the room temperature, which is about 50 degrees. Get a nominal measurement on the diameter. Okay, and here we are inserting the shaft along with the liquid nitrogen. And we started at 4 minutes to 1 when we started there. Okay, it looks like it's boiling in there, but it really isn't boiling. It's just taking all the heat out of that metal. And you can see all the fog coming out of there. That's the liquid nitrogen off-gassing. And you can see how much vaporizing it's doing there. It's pretty good fog. You'll have to forgive my shaky camera there. I had to walk around because I couldn't get it all in one frame there, so I had to walk around with the camera. And about 14 minutes into the process now. Uh, First try, lining up the shaft with the bore. Setting her in. Did not go in. Try it again. Not working. Got something on the bottom of the shaft and maybe something in the bore also. Gonna have to clean it off. Mark's gonna clean the bore out. And we're going to clean the bottom of the shaft off also. Might have been a piece of grease or something in there. We had it cleaned off to start with, but things happen. And we'll set it back in the tank to refreeze again. Okay, refreezing it again now. Walk around, look at the clock here. About 24 minutes elapsed time so far. Second try. Kind of hard getting that overhead crane set right because it's a big crane. And there we go. You have a little wiggle. Down she goes. Give a final tap. And there we are. We're done. We got her. Wow, that was a job. Now it'll take several hours to warm back up again. I'm going to walk around and see what the elapsed time is here now. Yeah, a little bit too close here for focus. I got too close to the darn thing. Same thing on the top. Okay, total elapsed time, about 35 minutes. That's it.